Section 6.5 Bigram and trigram substitution. Another way to prevent Emily from using letter and contact frequencies to break your cipher is to perform substitution on bigrams or even trigrams. The simplest way to do this is with a tableau. For bigrams, you would use a 26 × 26 tableau, where each entry would be a bigram. Here is the start of such a tableau. The substitute for AA would be BL, the substitute for AB would be TC, and so forth. For trigram substitution, you might use a booklet with 26 such tableaus, one for each first letter of the trigram. This type of substitution can be used by itself, or it could be combined with another method, such as polyalphabetic substitution. Used alone, bigram substitution is rated 3, and trigram substitution is rated 4. Bigram substitution followed by polyalphabetic substitution with secret well-mixed alphabets is rated 5, and trigram substitution followed by polyalphabetic substitution with secret well-mixed alphabets is rated 6. Section 6.6 Hiding messages in images. An interesting idea dating back to about 1999 is hiding messages inside various types of data files on a computer. This is a modern version of steganography, Section 2.2. Let's look at one such method, hiding messages inside a bitmap or BMP file. Bitmaps are images that are stored pixel by pixel. The most common bitmap format represents each pixel by 3 bytes that specify how much blue, green and red color depth is in that single dot on the image. This is the device-independent order in the Microsoft standard for bitmap images. If you have trouble remembering the order, notice that blue, green and red are in alphabetic order. For example, 000 has no color, so it is pure black. 255, 255, 255 has maximum depth for all 3 colors, so it is white, and 25500 would be pure blue. Pixels are commonly represented in hexadecimal, so pure blue would be FF0000. In some computer languages, this is written $FF0000 or $FF0000', or even 0xFF0000, since 255 in decimal is FF in hexadecimal. In some languages, the order of the color components is reversed. For example, in HTML, pure blue would be #0000FF. The entire image may contain hundreds or thousands of rows of pixels, each row containing hundreds or thousands of pixels. It is not unusual for a bitmap to contain 3,000 rows of 4,000 pixels each. Such an image would have 12 million pixels and would require 36 million bytes of storage, plus 54 bytes of header information. That's why having many high-resolution images can fill up a computer's memory so quickly. The trick is to use the low-order bit in each component of the pixel to carry 1 bit of the message. This could go undetected because the difference between FF0000 and FE0000 or even FE0101 is barely perceptible to the eye. In a single pixel of a large image, it would be visually undetectable. Besides, half of the bits would not change value. When hiding a message in an image, it is essential that the file containing the image is transmitted exactly. The image must not be enlarged, reduced, cropped, rotated, skewed, compressed, or converted into another image format. The message can be enciphered with any method. However, if Emily suspects you are hiding the message this way, then it would not add any extra security. You would be paying the price of transmitting 8 bits of data for every bit of the message, with no corresponding benefit. If you simply took every low-order bit from each pixel in turn, the rating would be the same as whatever method of encipherment you use. One way of gaining some extra security from this scheme is not to use all of the bits, but to select certain bits from each pixel in some cyclic order. To do this, you use a string of octal digits. See the table in section 3.1, such as 1, 3, 7, 4, 6, as a key for selecting the message bits. This can be called a selection key. It has 5 octal digits, hence 15 selection bits. Start with the first pixel of the image and the first digit of the selection key. If the first bit of this digit is 1, put 1 bit of the message into the low-order bit of the blue component of the pixel. Otherwise, set the low-order bit to 0 or 1 at random. If the second key bit is 1, do the same for the green component, and if the third bit is 1, do this for the red component. Then repeat this for the second pixel and the second digit of the selection key, and so forth. Someone might think that when the key bit is 0, it is better to leave the corresponding bit of the image unchanged. This would result in less distortion of the image and make it harder for Emily to detect that it contained a hidden message. True, but if Emily suspects that you are using this method, then it will make it possible to determine the selection key. Suppose this is the case. Emily has intercepted your message containing a bitmap image. Further, suppose Emily has done an image search on the internet and found the original image. Emily can match up the two images pixel by pixel and color component by color component. This enables Emily to make a map of where the two versions of the image differ. Everywhere the low-order bits match, Emily can mark an X in the map, and everywhere they do not match, Emily can mark a vertical line. Emily can then try each possible length for the selection key. When the correct length L has been chosen and the marks are lined up at intervals of L pixels, then every column where the selection bit is 0 will contain all X's, while the columns where the selection bit is 1 will contain half X's and half straight lines. For example, again using the selection key 1, 3, 7, 4, 6, you might see for every column that contains a vertical line, the corresponding bit of the selection key must be 1. All other bits of the selection key are probably 0. With more rows in the difference map, the probability gets higher. For this reason, wherever the selection bit is 0, the low-order bit of the color component should be set randomly. Using a cyclic selection key, this method of hiding the message adds 2 if the rating of the underlying cipher is 1 to 4, or 1 if the rating is 5 to 8. The selection key could also be generated using the chained digit pseudo-random generator from section 4.5 using a qualified seed of 7, 9 or 10 digits. Use generated digits from 0 to 7 as selection digits. If the generated digit is 8 or 9, discard it and generate the next digit. It is not important here whether the pseudo-random digits are statistically random. The essential property is that the sequence of generated digits is longer than the message, measured in bits, so that Emily cannot match up sections of the ciphertext that have the same selection key. Using a chained digit selection key, this method of hiding the message adds 3 if the rating of the underlying cipher is 1 to 4, 2 if the rating is 5 to 7, and 1 if the rating is 8.